Hello, and welcome to this quiet place at the end of the day, where you can learn the strangest and loveliest facts about the planets orbiting other stars, even as you fall asleep. I'm so glad you found your way here tonight. Maybe today asked more of you than it should have. Maybe your thoughts are still holding on to something small that happened hours ago. Or maybe you simply prefer falling asleep somewhere out among other worlds to lying here watching the ceiling. However you arrived, you've arrived. And the only thing left on your list tonight is rest. So let everything loosen a little. Let your breath find its own slower pace without you managing it. Let your jaw unclench and your shoulders come down, and let your body feel heavy and weightless at once, the way it does just before sleep takes over. Nothing ahead of this will ask anything of you. My voice will stay low and unhurried from here to the end, and the music will stay soft beneath it. No rise, no sudden turn. Nothing that lifts you back to the surface. It can keep you company all the way through the night. Tonight, we're drifting far past our own small family of planets, out among the thousands of worlds we've found circling other suns. Some of them are so hot that iron drifts through the sky as vapor and falls again in the cooler dark. Some wander alone with no star at all, moving quietly between the stars for billions of years. Some are wrapped in a single ocean with no shore anywhere on them. None of it is going anywhere. We have the whole night. If these gentle journeys are becoming part of your evenings, a like or a quiet word below helps another sleepy soul find their way here too. And now, let's drift out slowly among the strangest planets in the galaxy. Let's begin with something calm and surprising. Rain does not have to be made of water. On a planet called WASP-76b, the daylight side is hot enough that iron turns to vapor and rises into the air. Winds then carry that vapor around toward the night side, where it cools enough to gather into droplets. It seems there may be weather there made of metal, not in the soft silver way the phrase suggests, but as an infernal circuit of heat and wind and cooling, running without pause on a world that always keeps one face toward its sun. Some planets sit so close to their stars that the ordinary idea of weather begins to come apart. The heat there is not merely fierce, it transforms what things are. Temperatures climb high enough to pull molecules into pieces and lift metals into the air, so iron and magnesium may drift through the atmosphere as gases. Astronomers call these worlds ultra-hot Jupiters, and they are remarkable places to watch chemistry behave in ways nothing at home can match. An atmosphere carrying ingredients that on any cooler planet would be sitting quietly in the ground. For a very long time, a sky with two suns in it belonged to storytelling. Then astronomy caught up. Some planets really do circle a pair of stars at once, tracing a wide path around both, while the two stars turn about each other. Kepler 16b was the first that truly caught the public imagination. A world where two suns would hang in the sky together. It gently changed the feeling of the universe. A planetary system does not have to be built the way ours is. It can be built around a partnership. Most planets belong to something. They keep to a star, move as part of a family, and travel through the galaxy in company. Rogue planets do none of this. They drift alone through interstellar space with no sun at all. Some likely formed around a star and were later flung out during a violent encounter with a larger planet or a passing star. Others may have formed alone from the beginning, more like very small, failed stars. Either way, they wander in darkness on journeys that can last for billions of years. The planet 55. Cancri E makes the Earth feel almost impossibly mild. It is rocky rather than gaseous, and yet it orbits so near its star that much of its surface may be covered in molten rock. Picture a horizon made not of water, but of liquid stone, glowing softly orange beneath a dark sky. It is probably locked with one face toward its sun, so that same hemisphere is heated over and over again. Astronomers have even found hints that it may hold an atmosphere released from its own hot interior. A year on Earth feels natural because it matches the rhythm of the seasons. Some planets complete an entire orbit in less than a single Earth day. They sit so close that they must travel enormously fast simply to stay in orbit at all, sweeping around again and again at distances that seem impossible from here. One lap, and the year is over. Another begins immediately. On a world like that, the star would fill much of the sky, and the phrase "next year" would lose almost all of its meaning. We tend to imagine planets as bright spheres, catching the light of their star. The planet TRES-2b does no such thing. It is among the darkest worlds known, reflecting less than 1% of the light that falls on it. Darker than coal, darker than black paint. Rather than sending starlight back into space, its atmosphere seems to swallow almost all of it, leaving only a faint, eerie glow from its own heat. It is a planet warm enough to shine a little, and still very nearly black. Earth feels like a water world until you set it beside what may exist elsewhere. Some planets could be wrapped in a global ocean, hundreds or even thousands of miles deep, with no continents, no shorelines, and no meeting place between land and sea. The descent there would not end on a rocky seabed like ours. The descent would simply continue, mile after mile, through water, growing steadily heavier and stranger, with the rocky interior sealed away somewhere far beneath. A world can be all sea. From the sky down to depths no light has ever reached. planet WASP-12b orbits so close to its star that gravity is slowly pulling it out of shape. Instead of holding a near sphere, it appears stretched by tides into something closer to an egg. The same pull is drawing gas away from its outer layers toward the star, so the planet is being slowly consumed by the very sun it orbits. Its year lasts a little over a day, which tells you how near it must be. We are used to thinking of planets as settled things. This one is still being reshaped. Not long ago, planets seemed easy to picture. Rocky worlds close in, giant ones farther out, moons and rings, and one tidy arrangement to measure everything against. Then the discoveries began arriving, and that picture opened up. Astronomers found giants hugging their stars, worlds circling two suns, planets darker than coal, surfaces of molten rock, and wanderers with no star at all. More than 6,000 planets are now confirmed, with many billions expected across the galaxy. Our own system stopped being the template and became one example among countless others. A few planets are so swollen and airy that they seem barely possible. They can be as wide as Saturn, while holding astonishingly little mass, so little that, given a large enough ocean, one might float in it. Astronomers call them superpuffs. They appear to be small cores wrapped in enormous envelopes of hydrogen and helium that balloon far outward where the gravity grows weak. Kepler 51b is the best known, the breadth of a giant, and something closer to the substance of spun sugar. When a planet orbits close enough for long enough, the pull of its star can slow its spin until the same face is always turned inward. One side then lives under a sun that never sets, and the other under a sky that never brightens. This is not a rare arrangement. It may be common among close-in planets. The lit hemisphere can grow hot enough to soften rock, while the far side falls away toward temperatures cold enough to freeze gases out of the air. Between them lies a band of permanent twilight. On the hottest rocky planets, the air may not be made of water vapor or nitrogen at all. It may be made of stone. When a world sits close enough to its star, surface rock can heat until it melts and begins to evaporate, filling the sky with mineral vapor, sodium, silicon monoxide, and other gases lifted straight from the ground. In some places, that vapor may rise, cool, and return as fine grains of condensed rock. We tend to keep land and sky in separate categories. There, the land becomes the sky. A few planets are being slowly unwrapped by the stars they orbit. On a world called GJ436b, observations suggest hydrogen is escaping into space in an enormous cloud that trails behind the planet, rather like the tail of a comet. The process is far too gradual to see directly, but astronomers can detect it in the way that escaping gas absorbs starlight as the planet passes in front. Over immense stretches of time, a planet can be worn down by light itself. When astronomers speak of alien weather, they are not being poetic. Some planets may host winds that move faster than sound. These are not breezes or storms in any earthly sense, but global rivers of gas, fast enough to turn weather into something closer to planetary violence, driven by the enormous difference in temperature between the side facing the star and the side turned away. On certain hot giants, those winds may reach several thousand miles an hour in the upper atmosphere. They leave fingerprints, too, shifting the hottest region away from the point directly beneath the star. And that shift can be measured from light years away. Clouds are simply whatever the local conditions allow to condense. On Earth, that usually means water. On a much hotter planet, the ingredients are entirely different, and clouds may form instead from silicates, the same broad family of materials that makes sand, rock, and glass. High in the atmosphere, where temperature and pressure find the right balance, those substances can condense into fine mineral grains and drift like weather. A cloud is not defined by softness. It is defined by staying aloft, and powdered stone will float if a world is strange enough. Some rocky planets orbit so close to their stars that the surface never fully hardens. Instead of continents and seas of water, they may hold wide pools of molten rock spread across the daylight side, like glowing inland oceans. On a world such as Ketu 141b, a horizon might be made of moving fire rather than breaking waves. Rock vapor may rise from those pools, travel, and settle elsewhere as it cools, which means the line between geology and weather stops being a line at all. When a star like the Sun reaches the end of its life, it swells, gently sheds its outer layers, and leaves behind a small, dense ember called a white dwarf. Much heavier stars end another way, collapsing into something denser still. Either way, the discovery of planets around those remnants is remarkable. Many of them should have been swept up during the transformation. And yet, there they are. Either they survived very long odds, or they formed afterward out of the debris that was left behind. Both possibilities are astonishing in their own way. There is one planet that sounds almost like a legend. It circles a pulsar with the catalog name PSRJ1719-1438. And some astronomers think it is the hardened core of a companion star that was slowly stripped away until only its center remained. If that reading is right, it is not an ordinary planet at all, but the remnant of a star recast at planetary scale, carbon-rich, and under such pressure that the phrase diamond world entered the language. Whatever it turns out to be, a world was made there from the end of something else. It is easy to picture landing on a planet, even a hostile one. The imagination always goes looking for ground. Some worlds simply do not offer any. A gas giant has no true surface in the earthly sense. Its visible clouds are only the beginning of a descent into thicker and thicker layers, where pressure climbs, hydrogen shifts into forms that have no everyday name, and the atmosphere gradually becomes something more like a fluid. The idea of down would survive there. The idea of a floor would not. There is a limit to how close a planet can come to its star before tidal forces begin to pull it apart. And a handful of small rocky worlds are found sitting almost exactly at that edge. The tightest known orbits take only 4 or 5 hours from beginning to end. What makes them remarkable is not the speed, but the survival. Solid bodies holding together in a place where earlier models suggested nothing should last. They sit right at the boundary, and they are still there. The sun is middle-aged as stars go, and some planets orbit stars far older. One of them circles a pair of stellar remnants in an ancient globular cluster, and the system may be around 12 billion years old, which is why it has been nicknamed Methuselah. A planet that old would have existed while the Milky Way was still young and the heavier elements were still rare. It suggests that the universe has been assembling worlds for nearly as long as it has had stars, and makes our own feel wonderfully recent. Not every planet shines only with light borrowed from its star. Some young and massive worlds still carry enough heat from their own formation to glow in the infrared, radiating energy outward from deep inside. That warmth is left over from the violence of coming together, gas crashing inward, material slamming together, gravity pressing the interior, and it can linger for millions of years afterward. These planets are not cold silhouettes in the dark. They are embers of their own making, still slowly cooling. The word ice suggests something pale and brittle, cold enough to crack underfoot. Deep inside certain planets, it means something else entirely. Some worlds seem to sit between the rocky planets and the gas giants, with a core wrapped in enormous layers of high-pressure ice, water locked into crystal forms that do not occur naturally anywhere on Earth's surface. It can be hot and still be ice, because it is the pressure holding it there. A planet's hidden middle may be a whole kingdom of crushed and unfamiliar ice. Gravity is not only a force that holds planets in orbit. At close range, it becomes a sculptor, working in both directions. Some giant planets travel near enough to raise tides on the star itself, tugging gently at the stellar surface while the star pulls the planet out of round. From our distance, the effect is subtle, but the relationship is not. In these systems, the boundary between star and planet feels less tidy than it does at home. They are not passengers. They leave marks on the suns they circle. Locking one face toward a star does not always make a furnace. Farther out, on a cooler world with a thin atmosphere, the permanent night side can become a place of extraordinary cold, because heat has no efficient way to travel there. Gases could freeze onto the ground and never lift again, building slowly in the dark. A planet like that would carry two climates written directly into its geography. One hemisphere holding warmth, the other slowly collecting a winter with no end to it. The very first planet found orbiting an ordinary sun-like star was a surprise nobody had prepared for. In 1995, two Swiss astronomers announced that a giant world was circling the star 51 Pegasi once every 4 days, impossibly close, where no giant was supposed to be able to form. It overturned the expected picture in a single evening, and it opened everything that followed. They received the Nobel Prize for it 24 years later. On some locked worlds, the division is softer than it sounds. If the atmosphere is thick enough, winds can carry warmth around toward the shaded hemisphere, so the far side never becomes a perfect ball of ice. It stays dim and cool and starved of light, but not frozen solid. What you get is a planet arranged as a gradient rather than a split, brightest at the single point directly beneath the star, dimmest at the point exactly opposite it, and everything in between shaped by moving air. On Earth, sunrise and sunset are among the deepest rhythms there are. They shape sleep, migration, weather, and the emotional texture of a day. Some planets may never have either. On a locked world, the star would hang in one place, directly overhead near the center of the lit side, low and unmoving near the edges, and entirely absent on the far hemisphere. There would be no dawn arriving, no long shadows at a particular hour. Something we treat as universal turns out to belong only to local physics. Most stars in the galaxy are smaller, cooler, and redder than the Sun, a class called red dwarfs, and a great many of the planets we find, especially the small rocky ones, are orbiting stars like these. A planet there can circle very close and still receive only gentle warmth, because the star itself is faint. The star would sit larger in the sky than our sun does, and yet somehow gentler, giving off a fraction of the light and lasting for trillions of years rather than billions. A planet can sit in exactly the right place for liquid water and still have a difficult time of it because of the temperament of its star. Small red stars are often active, releasing flares and bursts of charged particles far more frequently than the sun does. On a nearby world, that could mean skies lit again and again by auroras that never quite become rare, and an atmosphere under steady pressure to hold itself together. Some of the most promising planets we know are orbiting some of the least settled stars. A planet often ends up somewhere other than where it was made. In many systems, the giant worlds appear to have formed far out where ice and gas were easy to gather, then drifted slowly inward through the disk surrounding their young star. That journey rearranges everything. A migrating giant can scatter smaller worlds, gather material as it goes, or settle its neighbors into precise repeating orbits. Some end up so close that they become hot Jupiters, enormous planets now sitting in a place where they could never have formed. For all the thousands of planets found beyond our solar system, not one moon among them has yet been confirmed beyond real doubt. That is surprising, given how common moons are here. Jupiter and Saturn are surrounded by them, and even small bodies keep companions. So astronomers keep looking for the faintest hints, tiny changes in timing, small shifts in light, a slight wobble suggesting something is circling a planet we can barely detect in the first place. Somewhere out there, alien moons almost certainly exist. Some planetary systems make our own feel spacious. Astronomers have found stars surrounded by several full worlds, all crowded inside a region smaller than Mercury's orbit. From the surface of one, if there were a surface to stand on, the neighboring planets would loom far larger than Venus ever appears from here. In arrangements like that, gravity writes a more intricate score, each planet feeling the pull of the others, their orbits settling into delicate patterns that can hold steady for ages, provided each one keeps its place. The tightest known family of planets is the TRAPPIST-1 system, where 7 Earth-sized worlds circle a small red star on paths that would all fit comfortably inside the orbit of Mercury. Because the star is so faint, those tight orbits do not automatically make furnaces of them. The planets pass one another at close range and tug in rhythmic patterns, locked into a chain in which each one keeps time with the next. It gives the whole system an almost musical quality, a tiny sun holding a family of worlds in step. When a star like the sun grows old, it swells into a red giant large enough that nearby planets should be swept up entirely. Some evidence suggests a few worlds may last a while, even after they enter those expanded outer layers. Survival there would not be peaceful orbiting. It would mean moving through a vast stellar atmosphere, slowed by friction, spiraling gradually inward, and stirring the star from within as it goes. The final chapter of a planet's life can be written inside a sun. On Earth, seasons come from the tilt of our axis, which gives us a gentle, dependable cycle. Some planets may lean far more steeply, with one pole pointed almost directly at the star for part of the year, while the other sinks into a long darkness. Such a world would not have anything like spring, summer, autumn, and winter. It would swing between long stretches of steady heating and long stretches of deep cold, with the star tracing a path across the sky that would seem entirely unfamiliar. Some planets follow long-stretched orbits that carry them in close to their star, and then far out again. So a single year can hold enormous swings in warmth and light. A world like that might spend part of its orbit in relative chill, and then sweep inward for a season of intense heating, with its atmosphere expanding and its chemistry shifting as it goes. A year does not have to be a steady cycle. It can be an event that arrives and passes. A planet does not need to hug its star to become warm. If its orbit is stretched, or a large neighbor keeps pulling on it, the world can be flexed over and over as it travels, and all that gentle kneading heats it from the inside. Astronomers call it tidal heating. We have a modest example at home in Jupiter's moon Io, which is the most volcanically active place in the solar system for exactly this reason. On some planets, the effect may rival the warmth arriving from the star. There may be worlds where volcanoes are not occasional events, but a permanent feature of the landscape. If tidal heating, youth, or internal chemistry keeps magma rising often enough, the surface is continually renewed, fresh flows darkening and cracking, only to be opened again by newer ones. A planet like that would never look old. Craters would be erased, the crust would stay young, and the atmosphere would keep being refilled from below. Geology there would not be a slow story. It would be the main event. Earth's crust feels ordinary only because it is home. In truth, the minerals that dominate our planet reflect one very particular history of temperature, chemistry, water, and moving plates. Change those ingredients, and a different kind of rocky world appears. Some planets may have crusts rich in minerals that are rare at Earth's surface, shaped by hotter conditions, unusual proportions of elements, or the complete absence of weathering by water. Even stone, it turns out, tells a different story from place to place. On some rocky planets, midday temperatures may rise high enough to melt the ground. This is not the warmth of a desert or the heat around a volcano. It is a noon so intense that rock can soften and flow across the surface in molten patches. Minerals can lift into the air, and the line between land and sky begins to blur. It changes the meaning of daylight rather completely. We think of noon as the bright middle of the day. There it is, closer to a furnace opening overhead. Darkness on another world does not always mean blackness. On a planet with active volcanism or molten regions, the night side may be lit from below, by lava flows, by glowing cracks, by heat rising from rock that has only just arrived at the surface. Imagine standing beneath a sky of stars while the land around you shines faintly red in branching lines. No moon required, no sunrise coming. The light belongs to the planet itself, which is a very strange kind of company. Some distant worlds may look frozen from the outside while hiding something remarkable underneath. If a planet or a large moon holds enough internal warmth from radioactive decay or from being flexed by a neighbor, a thick shell of surface ice can cover a deep liquid ocean below. The ice would not be a crust so much as a roof, sealing that ocean away from space and keeping the heat in. In our own system, Europa and Enceladus make this feel close at hand rather than theoretical. Earth's oceans are vast, and still they are interrupted by continents that shape currents, weather, and the whole history of life here. Some planets may have no land at all. Their surface could be one continuous sea, unbroken by coasts or mountain ranges or river mouths. From a distance, such a world might look serene, a round blue thing with clouds drifting above it. But with no shoreline anywhere, the chemistry and the weather would follow paths quite different from ours. Earth is not the only recipe for a rocky world. If a planet forms in a region where carbon is unusually abundant compared with oxygen, it may be built on a different chemical foundation altogether. Instead of the silicate geology that dominates here, such a world might hold far more carbon-bearing material woven through its crust and mantle, changing the minerals at the surface and the way heat moves through the interior. A rocky planet does not have to mean an Earth-like one. Deep inside a carbon-rich planet, the pressure could do something remarkable. Carbon squeezed hard enough locks into the crystal structure we call diamond, while shallower layers might hold graphite and other carbon-heavy materials. This does not mean a sparkling jewel waiting to be collected. It means a world whose interior architecture is shaped by the same element that makes both soot and gemstones here, stacked in layers under a weight that has no comparison at the surface. A star does more than shine. It also sends a steady stream of charged particles outward. And on some planets, that wind is strong enough to wear away the atmosphere itself. Worlds orbiting close to active stars are the most exposed. Over long stretches of time, the upper air can be heated, given an electric charge, and stripped away into space, as though the star were not only shining on the planet, but slowly stealing it. Astronomers watch it happen and learn from it. The escaping gas reveals both the strength of the star and the fragility of the planet's sky. Among the more curious planets are small, dense ones that may once have been much larger. Astronomers think some of them began as gas-rich worlds, wrapped in thick atmospheres, and then intense radiation and stellar wind blasted those outer layers away over billions of years. What remains is the hard center, an exposed planetary core, the survivor of a very long process of loss. There is even a gap in the sizes we find, as though a whole population of worlds slowly crossed from one category to another. One planet, catalogued as TOI 849b, may be the clearest case of all. It is about 3 times the width of Earth, and yet holds nearly 40 times its mass, which is far too dense for anything that could have kept a normal atmosphere. Astronomers think it is the naked core of a gas giant, a world that either lost its outer envelope entirely or never managed to gather one. It gives a planet a kind of biography, not only its formation, but how much of it has since been taken away. We tend to imagine planets circling above their star's equator, because that is how our own system is arranged. Some giant planets break that habit entirely. Their orbits are steeply tilted, and a few may pass almost over the poles of their star, moving on paths that would look sideways compared with the flat layout we know. It turns a solar system from a neat disk into something three-dimensional, and it usually means the system went through a long rearrangement early on. Stranger still, a few planets orbit backwards. Their motion runs counter to the spin of the star they circle, which is very hard to arrange if a planet simply forms in place from a rotating disk and stays there. WASP-17b was one of the first found doing this. Something must have tipped it over, a passing star or a long tug of war with another giant, and left it traveling against the grain ever since, permanently out of step with everything around it. A planetary system can look settled for millions of years and then rearrange itself. When several giant worlds form together, their gravity begins a slow contest of nudges and near passes. One orbit shifts, then another. A resonance gives way. An encounter happens. And in that moment, a planet may be sent outward hard enough to leave the star behind entirely. This may be one of the main ways rogue planets are made, a world born into a bright young family and eventually released from it. A planet with no star sounds like it should be frozen through. Some rogue worlds may keep a faint inner warmth for billions of years, all the same. The source would not be sunlight, but the slow decay of radioactive elements deep inside, together with heat left over from the planet's own formation. Sealed beneath rock or ice, that warmth could linger like an ember. A world does not need a sunrise to hold on to a little energy of its own. there may be more rogue planets in the galaxy than there are stars. Micro-lensing surveys, which catch a world only in the brief moment its gravity magnifies a background star, keep turning up free floating objects at a rate that suggests a very large hidden population. Nobody has a firm number yet, and the estimates keep moving. But it raises a quiet possibility that most of the planets in the Milky Way are not orbiting anything at all. The phrase liquid water usually brings sunlight to mind. A rogue planet may not need any. Beneath a thick atmosphere or under a shell of insulating ice, its own internal heat could be enough to keep water liquid far below the surface. That would mean one of the ingredients we care most about existing on a world where no sunrise has happened in billions of years. An ocean in permanent darkness, sealed away and holding steady. Habitability may depend less on where a planet is than on how it is built. And if you're still here, about halfway along, nothing is going to change. My voice stays exactly where it is. The music stays underneath it, and there is nothing ahead that rises. You can stop following whenever your body decides to. The rest of it will keep drifting along beside you. Many stars are born with a companion rather than alone. And that companion can twist the surrounding disk of gas and dust into odd shapes long before any planet has finished forming. Instead of a flat, orderly pancake, the material may end up warped, tilted, or split into separate rings that do not line up with each other. A planet growing in a place like that would inherit an unusual orbit from the very beginning, not from later upheaval, but from an unusual childhood. In a system with two stars, the suns do not sit politely still while a planet circles them. They move around each other, each pulled by the other, tracing their own loop around a shared center. A planet there must live with two sources of light that are constantly changing position. Sometimes the two would appear close together in the sky, sometimes far apart, sometimes one setting while the other still burned above the horizon. Even so, some of these orbits hold steady for ages. On Earth, shadow is a simple thing because one sun means one direction of light. On a world circling two stars, it becomes theatrical. If the suns are far enough apart in the sky, an object could cast two shadows at once, each pointing a little differently, and each shifting as the stars move. One might sharpen, while the other softens. At times, they would overlap. At others, they would stretch apart across the ground. Even an ordinary afternoon would arrive in layers. Stars keep their own habits. Some brighten and dim in regular cycles. Some release sudden flares. And some pulse gently as their outer layers swell and settle. A planet circling a star like that would live beneath a sky where the source of light itself is changing, where daylight strengthens and fades, not because of clouds or seasons, but because the star is doing it. Sometimes, the strangest thing in a planetary system is not the world at all. It is the sun above it. A pulsar is what remains after a massive star explodes and its core collapses. An object so dense and so rapidly spinning that it sweeps beams of radiation through space like a lighthouse. Planets there do not orbit warm sunlight. They orbit the aftermath of a catastrophe. The first confirmed planets beyond our solar system were found circling one of these back in 1992, which still feels remarkable. They do not orbit warm sunlight. They orbit the quiet aftermath of something enormous. And their existence permanently widened our sense of where worlds can exist. When a massive star reaches its end, the release of energy is beyond ordinary comparison, and the whole system is transformed in a matter of hours. And yet, some planets may come through it, particularly those orbiting far enough out or fortunate in their timing. Coming through would not mean remaining unchanged. Atmospheres could be stripped, orbits reshaped, the system left in the keeping of a neutron star. Even so, the planet continues. It carries on through an explosion that briefly outshone an entire galaxy and keeps to its silent orbit long afterward. Not every orbit lasts forever. Some close-in giants are slowly losing energy through their gravitational exchange with the star, which means their paths are very gradually shrinking. WASP 12b is the clearest case measured so far. Its year is growing shorter by about 30 thousandths of a second each year, which does not sound like much until you follow the arithmetic forward. The star raises tides in the planet raises tides in the star, and a little energy leaves the orbit each time. Gravity does not pull equally on every part of a nearby world. If a planet orbits very close to its star, the near side feels a stronger pull than the far side, and that difference is what we call a tidal force. Strong enough, it stretches the planet into something slightly oval rather than round. It also flexes the interior, generates heat, holds the rotation in place, and shapes the atmosphere. A close planet is not merely warmed by its star, it is handled by it. Past a certain point, the pull of a nearby star begins taking a planet apart altogether. Astronomers have found small worlds that appear to be shedding material orbit after orbit, trailing long clouds of dust behind them, like a comet. The transits are never quite the same twice, because what is passing in front of the star keeps changing shape. A planet does not always end with impact or fire. Sometimes it is torn apart slowly, piece by piece, by the same gravity that once held it in place, becoming a trail of dust that still circles faithfully as it goes. We usually expect the lightest gases to escape a planet first, hydrogen above all. On the hottest worlds, astronomers have found something more surprising. On WASP-121b, signs of magnesium and iron have been detected high in the atmosphere, apparently on their way out. That means the upper layers are being heated and stirred vigorously enough to carry metals upward into the region where they can be lost. In a sky like that, the difference between air and departure begins to blur. One of the quiet triumphs of modern astronomy is that we can read the chemistry of worlds we will never visit. As a planet passes in front of its star, a thin sliver of starlight filters through its atmosphere, and different molecules leave different marks on that light. This is how signs of water vapor, carbon dioxide, sodium, potassium, and various metal-bearing gases have been found in distant skies. A planet stops being a dot in a catalog and becomes a place with air and weather. Reading a planet's air has recently become fine enough to notice differences around a single world. On a locked world, the edge turning into daylight and the edge turning into night may not share the same chemistry because gases form, break apart, and condense depending on where they are. One edge has just come out of the cool dark. The other has spent the whole passage under the full weight of the star. We are no longer only asking what a planet's air is made of. We are asking how it varies as you travel. A planet does not need continents to build an enormous storm. In fact, some of the largest and longest-lived storms may arise on worlds with deep, uninterrupted atmospheres, where energy can circulate for years without ever meeting land. We have a persistent example close to home in the Great Red Storm on Jupiter, which has been turning for something close to 200 years. On hotter or faster spinning giants, a storm might become less like weather and more like a permanent feature of the planet's identity. From far away, a cloud-covered planet can look almost restful. Clouds soften a world and hide whatever lies beneath. On some giants, that softness is a kind of screen. High in the atmosphere, clouds of exotic material drift through relatively cooler layers, while far below them, the temperature climbs into something else entirely. The visible cloud deck becomes a false surface. What looks pale and gentle from outside may be sitting above pressures and heat with no comparison anywhere on Earth. Astronomers often want to look deep into a planet's atmosphere, and some worlds simply decline. They are wrapped in high hazes of very fine particles that scatter light so effectively that everything beneath is hidden, and the measurements come back oddly flat and featureless. The planet is there, the atmosphere is there, and the detail is behind a curtain. It is a beautiful sort of frustration, a world keeping its own secret by growing a veil, like a face seen through frosted glass. Nobody has ever stood on a distant planet and taken a breath. But chemistry lets us imagine what the air might carry. On a hot, rocky world with volcanic gases rising, sulfur compounds could dominate, giving the sharp scent of a struck match. On a scorched giant with metals in the upper air, the air might be harsher, closer to hot machinery. On worlds where mineral vapor lifts from molten ground, it might be something like stone dust and ash. Smell is such an intimate sense that the thought makes a distant world suddenly physical. Earth gave us rain, snow, hail, fog, and storm. Those words belong to one planet with one set of materials and one narrow range of conditions. Elsewhere, weather may work in combinations our language was never built to hold. A world with mineral clouds, metal vapor, supersonic winds, and permanent daylight on one side is not really having a storm. In any sense, we have a word for. Somewhere out there, the sky is doing something real and complicated, and we have no simple name for it yet. Density is one of the quietest and most revealing things we can measure about a planet, because it hints at what the world is actually made of. The range turns out to be enormous. At one end sit worlds lighter than cork, so extended that they are mostly atmosphere. At the other sit small, stripped planets denser than iron, compressed by their own gravity into something remarkably compact. Two planets can be the same width and be entirely different objects underneath. One of the quieter conclusions of the last 30 years is that planets are ordinary. From counting how often they turn up, astronomers estimate there is, on average, at least one planet for every star in the galaxy, which means something like 100 billion of them in the Milky Way alone. And most stars you can see are holding at least one. Planets are not the exception that our own system once made them seem. They may be what stars usually do. Astronomers sometimes find planets that are simply too large for what they contain. Their measured width is greater than their mass, and age should allow. And by the usual models, they ought to have cooled and contracted more by now. Yet there they are, still inflated, as though something were holding them open from within. Perhaps radiation from the star is being absorbed more deeply than expected. Perhaps energy moves through the interior in some way we have not pinned down. It remains a lovely, open question. The smallest planet we have found is smaller than Mercury. Kepler 37b is only about a third the width of Earth, barely larger than our own moon, and it circles a star some 200 light years away. Finding it at all required noticing a dip in starlight of a few parts in 100,000. There is something lovely in that. Among all the extremes and record holders, we have also managed to pick out one very small, very ordinary rock. Most planets are found indirectly through a dimming, a wobble, some small effect on their star, which is why a direct picture feels so different. In a handful of cases, astronomers have blocked out the starlight and captured actual images of giant planets glowing beside their suns. The system HR 8799 gave us the first family portrait. 4 worlds, visible at once, moving slowly along their orbits over the years. It is like noticing a firefly beside a floodlight from across a continent, and we have managed it. Some planets have been caught in the act of forming. In the disk around the young star PDS-70, astronomers have imaged 2 planets still sitting in the gap they have cleared, still gathering material from the gas around them. It is one of the most satisfying pictures in the field because it turns a theory of origins into something you can look at directly. Somewhere in that glow, a world is being assembled, and the process is not finished yet. Some giant planets circle at distances so great they feel almost detached from the star they belong to. Rather than hugging close, they travel on wide orbits, many times farther out than Neptune is from the Sun. From such a world, the star would look like an unusually brilliant point of light, rather than a sun that rules the sky. And any moons there would live in a dim outer kingdom where the planet's own warmth might matter as much as starlight. Giant planets on very wide orbits are genuinely provocative because building something so massive that far out should be difficult. Material out there is sparse and growth is slow, so the usual picture struggles to make one in the time available. That leaves 2 interesting possibilities. Either they formed where we see them by some other route, more like the birth of a very small star, or they formed closer in and were sent outward later. Both answers imply a livelier history than a calm disk would suggest. Sometimes a planet is found without ever dimming its star or being photographed. If one star passes in front of a more distant one, its gravity bends and briefly magnifies the light of the background star. Add a planet to the foreground star, and the pattern of that brightening changes in a way that gives the planet away. For a few days, gravity itself becomes the instrument. A world announces its presence by bending the geometry of light coming from far behind it. The most productive method is also one of the simplest. If a planet crosses in front of its star from our point of view, the starlight dips by a tiny fraction, and that dip reveals the planet's size and the length of its year. It depends on very fortunate alignment, so most planets never show themselves this way. But when one does, the effect is quietly moving. A world becomes known because, for a few hours, it stands in the way of the light. A star does not sit still while a planet orbits it. Both move around a shared center of gravity. And although the star's share of that motion is small, it is measurable, visible as a slight shift in its light as it moves toward us and away again. This was the method behind many of the first discoveries, and it gives us something the others cannot: a clue to the planet's mass. A world too faint to see still makes its star sway. Some planets are studied mainly through the heat they give off, rather than any light they reflect. Young giants, still warm from forming, radiate in the infrared, and that glow carries a surprising amount of information. Whether the atmosphere is cloudy, how the chemistry varies, how quickly the world is cooling. It is a different kind of acquaintance from a transit or a wobble. It feels closer to noticing the warmth of something in a dark room. Sometimes astronomers find no planet at all, only the marks one leaves behind. A disk of dust may show a sharp gap, as though something has swept a lane clear. A ring may be warped or lopsided. Gas may flow in a pattern suggesting an unseen sculptor. In older systems, one known planet's orbit may be slightly off, hinting that another is tugging on it from somewhere out of view. Planets are not only objects, they are agents, and they leave tracks. Planet formation is not only a story about the distant past. Around some newborn stars, the disks of gas and dust show rings, spirals, gaps, and clumps that look very much like the fingerprints of worlds in the middle of growing. When the great radio arrays first produced sharp images of these disks, the delicate rings came as a genuine surprise. We are no longer limited to imagining how planets once formed. In some systems, the architecture is emerging while we watch. Some systems settle into a kind of gravitational choreography. One planet may complete 2 orbits for every 3 of its neighbor, or some other repeating ratio that keeps their pulls organized rather than working against each other. Astronomers call it resonance, and it usually forms while planets are still migrating through the disk, locking together as they move. Once established, it can hold for an extraordinarily long time, a chain of worlds, each keeping time with the next. It is worth remembering how local our map still is. Almost every planet we know orbits a star within a few thousand light years of here, a small neighborhood in a galaxy 100,000 light years across. The methods we use simply cannot reach much farther. So the catalog is not a survey of the galaxy. It is a careful description of the houses on our own street, and even that has taken 30 years. A transit is meant to happen on schedule. If a planet crosses its star every 10 days, the next dip should arrive right on time, and in some systems, it does not. It comes a little early or a little late because another planet is tugging on it and nudging its orbit. Those small discrepancies are enormously useful. They can reveal planets that never transit at all. In astronomy, even arriving late can become a form of evidence. The systems we see today may be the survivors of much more crowded beginnings. Early on, many stars may have held additional worlds that later collided, fell inward, or were sent out into interstellar space. What remains can look perfectly calm, and that calm may be misleading. A star with 3 planets now might once have had 6, with close encounters gradually removing the rest. Some of the rogue planets drifting through the galaxy may be the missing members of exactly these families. Planetary systems can be rough with themselves in their youth, and sometimes long afterward. Worlds can cross paths and eventually meet. Some encounters shatter both worlds into debris. Others fuse them into a single larger planet built from fire and molten wreckage. Our own system carries the marks of an era like this. The Moon is generally thought to have formed from the aftermath of one enormous meeting. A quiet planet today may hold the material of another one inside it. Some of the planets we find appear to be survivors, rather than tidy examples of how planets are meant to look. A world might once have had close companions that were lost, or an atmosphere that was worn away in an earlier era, or an orbit reshaped by forces that removed everything else nearby. What remains is not the original design. It is the last one standing, and its odd density, or its lonely placement, may be all that is left to tell us what happened to the rest. Size is no guarantee of gentleness. Some planets smaller than the Earth orbit so close to their stars that their surfaces stay molten despite their modest scale. We are used to thinking of small worlds as dim and geologically quiet, and these overturn the instinct completely. Instead of an enormous inferno, like a hot Jupiter, you get a compact, rocky world glowing like an ember. Its day side soft with lava. A planet does not need to be large to be extraordinary. Some rocky worlds out there may be startlingly young, younger, in fact, than many lineages of life on Earth. While sharks and trees and insects trace their ancestry back through immense stretches of time, a distant, rocky planet may have only recently finished assembling from dust and impact, still cooling still sorting out its crust. New worlds are appearing, while old life carries on here, which makes the galaxy feel much less finished than it looks. Every time astronomers find a planet in a very young system, the timetable for planet formation gets gently rewritten. Some worlds appear to be there sooner than the cautious versions of theory once allowed, which suggests nature can build large bodies at surprising speed. This matters because the disk of gas around a young star does not last forever. If a planet grows large while that disk is still present, everything that follows, migration, atmospheres, resonances, happens differently. The phrase habitable zone sounds reassuring. It marks the region around a star where temperatures might allow liquid water at the surface, and that is genuinely useful, but it promises less than it seems. A world can sit right inside it and still be a difficult place. The atmosphere may be too thick and trap too much warmth. The star may be restless. The planet may be locked, with heat piling up on one side. The zone is a starting point, not a conclusion. On some worlds, the difference between a mild climate and an impossible one may come down to a few details working together. Thick clouds can reflect starlight and cool a surface. Tidal warmth can keep a world from freezing. A magnetic field can shelter the air from a restless star. Remove any single one of those, and the same planet tips the other way. Habitability is less a location than a cooperation. From a distance, an ocean world can look like the gentlest place imaginable. A smooth blue sphere with clouds drifting above an unbroken sea. Up close, it may be far more hostile. The ocean could be hundreds of miles deep, with pressures at the bottom beyond anything here, and a layer of high-pressure ice sealing that water away from the rock below. Cut off from the minerals in the interior, the chemistry many scientists think life needs may never quite get started. Some planets may be so hot and so rich in water that their skies never clear at all. Instead of open air above a sea, they may be wrapped in thick layers of steam, with the atmosphere itself becoming a hot, heavy shroud. Water is present in abundance, just not in any gentle form. The oceans keep feeding an envelope dense enough to block any direct view of the stars. It takes the most hopeful ingredient a planet can have and puts it somewhere quite unreachable. We think of rock as the solid baseline of a planet, but some worlds may never cool enough for that story to begin. If the star stays close and the temperature stays high, rain never forms, rivers never persist, and large regions of the surface never settle into ordinary stone. Molten rock and mineral vapor keep the upper layers in motion. There is no slow weathering of mountains, no valley carved patiently by water. The planet simply stays in an earlier chapter than ours did. Gravity shapes experience more than we usually notice. Every step you have ever taken was learned inside one particular pull. On a massive rocky super-Earth, gravity could be considerably stronger, so that walking might feel like climbing and lifting an arm would tire you sooner. On a smaller world, the opposite would hold. Falls would be gentler, movement springier, everything faintly untethered. Two planets can look similar in a catalog, while feeling completely different to a body standing on them. On some worlds, a day is longer than a year. It sounds impossible until you remember that we have an example in our own neighborhood. Venus turns so slowly that a single rotation takes longer than its trip around the Sun. On a planet like that, the usual units stop lining up in any comfortable way. Sunlight arrives through a strange contest between a slow spin and a faster orbit. And the words day and year lose their ordinary relationship to each other. We already live beside a tidally locked world, which is easy to forget. The moon keeps the same face turned toward us at all times, for exactly the reasons that lock distant planets to their stars. A long, patient gravitational exchange that gradually slowed its spin until it matched its orbit. Nobody on Earth has ever seen the far side with their own eyes. The strangest arrangement in exoplanet science has been hanging above us the whole time. On a locked planet, the most interesting region may be the narrow band between permanent day and permanent night. Astronomers call it the terminator zone, and there the extremes might partly cancel each other. Too far toward the star, and the ground overheats. Too far into the dark, and everything collapses toward cold. But along that ring, the two could balance. It is a lovely thought. A world might keep its most temperate ground not in a hemisphere, but in a thin circle drawn between two conditions. The color of daylight depends entirely on the star. Around a cool red dwarf, the light reaching a planet is shifted toward longer wavelengths, so the whole world would be lit in a way quite unlike Earth's blue-white afternoon. The sky's actual color would depend on the atmosphere, but the overall illumination could feel dimmer, warmer, more coppery. The same mountain, the same ocean, the same bank of cloud would carry a different mood under a deeper red sun. At a certain point, the word planet starts to feel a little mild. Some worlds are so hot and so thoroughly reworked by nearness to their star that they behave more like blast furnaces than like places at all. Their atmospheres may hold vaporized rock and metal. Their daysides may glow. Their winds may run at speeds nothing here can match. Calling such a world a planet is entirely correct. It simply stretches the word further than everyday use has ever needed to. Here is something gently upside down. A few planets are hotter than some stars. The day side of an ultra-hot Jupiter, such as KELT9b, can reach temperatures above those found at the surface of many small, cool stars. That does not make it a star. It lacks the mass and the fusion that would define one. But it does show how misleading our categories can be. A planet can be the lesser object by every structural measure and still be the hotter one. Astronomy has followed the same pattern again and again. First comes the idea that a certain kind of planet would be too strange or too unlikely to exist. Then comes the discovery that nature made one anyway. Giants skimming their stars, worlds around pulsars, densities that seemed absurd, rocky bodies with molten faces, systems packed far tighter than theory preferred. The catalog of known planets is, among other things, a long and gentle record of corrected expectations. There is something worth carrying with you the next time you happen to be outside after dark. A great many of the stars you can pick out with your own eyes are now known to hold planets, and most of the rest almost certainly do. Vega has a wide ring of dust around it. So does Fomalhaut. The point of light, you notice, without thinking about it, is not a lamp on its own. It is a household, and people have been looking up at those worlds for as long as there have been people, without ever knowing they were there. And for all the remarkable worlds already known, we are still very early. Our methods favor certain kinds of planet. Large ones, close ones, systems aligned just so. The catalog is a first draft shaped by what our instruments find easiest to see. Somewhere beyond that lie worlds stranger than any we have met, with combinations of chemistry and orbit and structure nobody has thought to imagine yet. The strangest planet may not be famous. It may simply be waiting, unbothered, in the dark. We've come a long way tonight, and there is nothing left to do with any of it. Iron falling as rain on the cool side of a world that never turns. Oceans with no shore anywhere on them. A planet drawn gently out of round by the star it circles, and others wandering alone in the space between stars, keeping a little warmth of their own for billions of years. They will all go on exactly as they are while you sleep. The metal weather, the twilight rings, the slow, wide orbits out where a sun is only a bright point among the others. Nobody has to be awake for any of it. And if you slipped away somewhere back among the lava fields or out with the wanderers, then you got exactly what you came for. There is nothing here to finish. Thank you for spending part of your night with me on the Nightly Science Journal. Come back another evening and we'll wander somewhere else just as slowly. Let your breath go quiet now. Let those distant worlds dim and drift off to the edges of your mind. Let the rest of the way happen on its own. Sleep well, and good night.